The first one we're going to look at is geothermal energy. So what is geothermal energy? Geothermal energy is heat from the earth. So it's heat coming off of magma chambers, working its way up to the surface. So you can use geothermal heat by using the water that's being driven off of those magma chambers. The hot water that's reaching the surface, so where you find things like hot springs, that's an area that's perfect for geothermal energy. So you use the water heated by the earth generally to generate steam and turn turbines to generate electricity. So just like nuclear energy, just like a coal-fired power plant, you're just using steam to turn a turbine, and in this case, the steam is generated from the heat of the earth. The water is commonly kept under pressure until it's piped to a turbine. When pressure is released, the water flashes into steam and turns the turbines. And what sites are most favorable for its use? So in this image, it's showing shallow magma. So that means magma that's close to the surface is ideal. So areas that were recently active. Also, it's good to have faults in the area because hot water is going to work its way up to the surface along those faults. And in those areas, you're going to get things like geysers and hot springs, and that's how you'll know that is a geothermally active area. So again, what sites are favorable for its use? Areas of recent volcanism or tectonism, meaning plates have been shifting around, earthquakes, are most favorable. And the warm to hot water can also be used for local heating. Another alternative source of energy is wind power. Wind power is when you're using the wind to turn turbine blades that are directly hooked to the generator. So again, same concept, turning a turbine that's powering a generator, but in this case it's just the wind. So strong winds that blow most of the time are needed, and wind power is a renewable, non-polluting source of energy. Wind turbines are not aesthetic. That's one of their drawbacks. Some people think that it ruins their view, or it ruins this landscape to put up a bunch of wind turbines. They also can be very noisy. They create a lot of sound as the wind is blowing through them, and they're expensive to maintain. Excuse me. And another argument against them is that they do kill birds. So if you have a big migration or something going through these areas, it can be hazardous. And depending on the species, if it's something that is having trouble keeping its population up, that can be a big deal. All right, but otherwise, it's renewable and non-polluting, so those are its advantages. Then we have passive solar heating. We've got a couple different types of solar that I want to talk about. So solar energy how is solar energy used? Solar energy uses the sun's electromagnetic energy to heat buildings, heat water, and generate electricity. Okay, so breaking that down into passive and active. Passive solar heating is something that's really common in cold areas especially. So passive solar heating uses light and infrared energy. Sunlight enters a space through glass and heats the air inside. So it's all about orienting your building properly so that it's getting the optimal amount of sunlight in the wintertime, so that the building can retain that heat. Okay. Active solar heating uses fans to move heated air or pumps to circulate heated fluids from solar panels to the interior. So if you've got solar panels on your house, then you're doing active solar heating. So you're moving heated air to circulate the energy from the panels down into the space that it's heating. Some other alternative sources, biomass is the burning of wood or decaying organic material. Fuel cells is where we break water into hydrogen and oxygen, and it's releasing energy from that. So this is thought to be the fuel of the future. And so when we're talking about hydrogen cars and things like that, that's what we're talking about. Ethanol is a type of alcohol produced from corn, sugar cane, or other plants. Really any plant that can generate a sugar can be turned into ethanol. And so ethanol can be used as fuel in place of gasoline. And you also have biodiesel, which can be used in place of diesel fuel. How is nuclear energy produced to generate electricity? Okay, if you said uranium decays into two smaller particles, releasing heat in the process, you would be correct. So remember, we're triggering radioactive decay. This is fission. The particles are breaking apart and releasing heat in the process. So that heat heats up water, generates steam, and turns a turbine. So let's look at the other answers and see why they weren't options. So the first one, lead is heated until it becomes molten and turns into uranium. No. That makes no sense at all. Okay, lead and uranium don't have anything to do with one another. Number two, hydrogen and helium are combined in the process of nuclear fusion. Okay, no. That's the sun. Fusion is the sun. We haven't figured out how to do it yet. Number four, large panels collect light from the nuclear-powered sun. No, that's solar power, right? And so that doesn't work. So it should be three. Uranium decays into two smaller particles, releasing heat in the process. How do most uranium deposits form? So this is calling on the information from last week's lecture, so I hope you have it handy, or you've been studying it. If you said number three, uranium is transported and deposited by groundwater, you would be correct. Remember the image of the roll front, right, where the uranium is moving along in the water until it hits another body of groundwater and gets deposited along that contact. Also in the breccia pipe, it's all being moved by groundwater. Okay, so let's take a look at the others and see why they didn't work. Number 1, granites solidify, trapping uranium within the crystals. No, we didn't say anything about that, right? Number 2, volcanic pipes bring uranium to the surface from deep in the mantle. No, that one is a little bit tricky because it uses the word pipe, and you can find uranium in breccia pipes. But remember, a breccia pipe is from a collapse, right? And it's got those angled pieces of rock. That's why it's breccia. Volcanic pipes do not bring uranium to the surface from deep in the mantle. It's a surface process. And number 4, there are no natural deposits because uranium is produced in the laboratory. No, we know that's not true, right? We mine it from the ground. So number 3 is correct. Which of the following factors make a site more suitable for a hydroelectric dam? Okay, it should be none of the above, so let's go through and see why. Number 1, numerous faults and fractures that allow groundwater to flow into the reservoir. Okay, this might sound like a good thing because you're allowing water to flow into the reservoir, which means you're getting more water. But if you've got faults and fractures and you've got groundwater flowing around your reservoir, that means you can also lose all of the water that's in it, right? If it can flow into it through fractures, it can flow out of it through fractures. Number 2, permeable rocks next to and beneath the dam to keep pressures from building up. No, right? We do not want permeable rocks anywhere around our dam, really. So we definitely don't want them underneath the dam, so that you'd be losing all the water from below. But even next to the dam is going to cause a problem for losing water. So you always want to have impermeable rocks, meaning there's no faults, there's no fractures, there are no pore spaces. Water doesn't move through the rocks. So it's not that one. Number 3, a canyon that is wide so that a large dam can be built. Okay, this sounds like a good idea. Sure, who wouldn't want a large dam? But what you need in a dam is vertical height. So to be cost effective, getting a very narrow canyon is ideal. You want to be able to build the smallest wall possible across a canyon and have the largest amount of vertical drop, because it's that drop that is turning the turbines. Number 4, weak units in the abutments to make construction easier. No, no, no. We want to have strong rocks in the abutments. Remember, that's the side areas near the wall. And those need to be strong because you're building up lots of pressure with all that water. So if you've got weak rocks, it's not going to hold up. So none of these are correct answers. How is electricity generated from hydroelectric dams or ocean tides? Okay, water piles up behind a dam or tidal barrier and flows down because of gravity. Right? And it's that drop or flowing over that turns the turbine. And so gravity is what is doing all the work in both cases. Okay, let's look at the other ones to show why number 3 is the best answer. Number 1, water is pumped upward and then back down. No, because if you're pumping it, then you're using electricity to do that. So whatever you're generating, you're using. That would not work. Number 2, turbines are used to pump the water upward and generators produce the electricity. Again, no, you don't want to have to pump it upward. You've got to find a way to have it naturally fall. And so that's what's so great about a very narrow canyon dam or using the natural tides, because water's building up naturally. That brings us to the mineral resources part of the lecture. And the first question is, what is a mineral deposit? So just because there is a mineral somewhere doesn't mean that it's a mineral deposit in mining terms. Okay, so everything we're talking about here is in mining terms, and all of that has to do with the economics of it. So what is a mineral deposit? The rocks are especially rich in some commodity that might be valuable. Okay, so a mineral deposit contains something valuable. It can be mined and sold for a profit. A vein with only quartz, for example, is not a mineral deposit. Okay, in geologic terms, quartz is a mineral, and a quartz vein is an area of a mineral, but a mineral deposit is a term specific only to a valuable mineral. Ore, O-R-E, can be mined at a profit. So ore is what you're looking for in a mineral deposit. If the deposit contains enough of a commodity to be mined at a profit, we call it ore. Again, if the deposit contains enough of a commodity to be mined at a profit, it is considered ore. Okay, well, how do we consider, or how do we determine if the rock can be mined at a profit? How do we decide whether a rock is ore or not? Okay, the first thing we look at is the grade of the ore. That's the concentration of the commodity. Is it rich or high-grade ore versus low-grade ore? Okay, meaning does it have a lot of the commodity we're looking for, or does it have less of the commodity we're looking for and more of some other type of rock? Okay, so if it's a high concentration of the mineral we're looking for, that's high grade. If it's a low concentration, that's low grade. Okay, that's the grade of the ore. Then we have the type of ore. The type of ore determines how ore is processed. So oxide ore can be crushed and leached, but sulfides may need to be smelted. Okay, crushed and leached means it gets sent through a mill that has these big metal spheres in it that tumbles the rock around and breaks it up into little pieces. And then leached, usually the rocks are put in some sort of acid bath, or they're put in cyanide, and that leaches out the minerals from the rock. So it leaches out whatever it is of value you're looking for. and in the case of sulfide minerals, they may need to be smelted, so that means basically they get heated to very high temperatures. Okay, also in determining whether a rock is ore or not is the size and depth of the deposit. Larger and shallower are cheaper to mine. Okay, so that means they're more likely to be ore if they're closer to the surface and if they're a larger deposit. The location of a deposit, the proximity to infrastructure, so how far ore has to be transported, and the politics and environmental issues involved also determines whether a rock is ore. So for example, if there is a gold deposit right by Phoenix, then that might be ore. But if there is a gold deposit somewhere in the remote tundra in northern Canada, then that's less likely to be ore. Or if it's on some area that is politically unfavorable, so a country that we don't get along with, or a country that has unstable leadership, they're in a war or something like that, then that would mean that the rock is not ore. So all of these things determine whether a rock can be mined or not. Alright, now we're getting into the processes that form these mineral deposits. So hot or deep processes that form mineral deposits. The first one is igneous crystallization. Okay, this is when a magma chamber is cooling and it can concentrate minerals by crystals settling out of the magma chamber. Okay, that's igneous crystallization. Igneous crystallization can concentrate minerals by crystal settling. The next one is hydrothermal deposition. Okay, just like the name says, hydrothermal, this is from hot water, but it's usually from hot water along a fracture in hot springs or vents along the seafloor. So along the seafloor, they're what are called black smokers. They're these volcanoes that are on the seafloor and just spewing out mineral-rich water at very high temperatures, and you get big mineral deposits around there from the interaction of the heat and the minerals in the water and the cold, cold ocean water around it. But again, also hot springs or along fractures. So this would be fractures, especially coming off of magma chambers where you have mineral-rich waters coming off of the magma chamber. When it goes through a fracture, it tends to deposit minerals all along that fracture, and you get a mineral vein like that quartz vein we just looked at. We also have hydrothermal replacement. In this case, fluids permeate rock and replace the original minerals with ore minerals. Okay, you can also get mineral deposits during metamorphism. Metamorphisms, heat and pressure can allow new crystals to form. In this picture, we're looking at kyanite crystals. At one time, these were used for spark plugs, but these form under metamorphic conditions. And the last one here is volcanism and volcanic pipes. This can bring up precious minerals formed at depth, like these diamond pipes. So diamonds form very, very deep in the earth. They require a huge amount of pressure. They're just carbon. They're pure carbon, just like the graphite in your pencil. And the main difference is the amount of pressure that the diamond has been put under. So again, it needs very high temperatures, and then it gets brought to the surface through these very fast-moving, explosive volcanoes. And we don't need high pressure and high temperatures to form all mineral deposits. We can have superficial processes that form mineral deposits. So some of those are formation by weathering. So extreme weathering can leach away most material, concentrating less mobile elements such as nickel and aluminum. That's what's going on right here at this bauxite mine. They're mining out these heavier minerals that were concentrated as the surrounding material got washed away, basically, over many, many, many years. Weathering enrichment. Elements can be leached from rocks by weathering, carried by groundwater, and deposited elsewhere. Mechanical concentration. Transport in rivers or wave action on beaches can concentrate valuable minerals such as diamonds in these river gravels. Boy, I'd like to go by that river. This one is in South Africa, so it's not likely that you'll be walking by and just pick up these diamonds, but it does happen. Okay, that also happens with gold. So if you think about the old pictures from the gold rush of men out by a river panning for gold, that mechanical action of panning is the same thing as this mechanical concentration. So it's kinetic sieving. The heavy stuff gets left behind, and the lighter stuff floats away. And low temperature precipitation. So salt, gypsum, and other commodities can be precipitated in lakes and seas as they evaporate.